In this part of the Computational Intelligence course related to fuzzy systems, we will start to fuzzy relations. First, we will see the analogy between the crisp and fuzzy relations, and then we will see that the fuzzy relations are in fact fuzzy sets. We will also see the definition of Cartesian product on fuzzy sets, which is a relation on the fuzzy sets. A crisp relation represents presence or absence of association, interaction, or interconnection between elements of more than two sets. We are trying to define the relation x is less than y. Here 2 is less than 3, 4, 5, so 2, 3, 2, 4, and 2, 5 are the elements of the relation. 3, 4, and 3, 5 are the elements, and 4, 5 are the elements of the relation. Or in a continuous space, x is between 0 and 10, then x is less than y can be defined as this region. And if we consider the relation as a set, any point here belonging to this region has a membership value 1, the relation has value 1, and for the other regions, the relation has value 0. This concept can be generalized to various degrees of strength of association or interaction between elements. A fuzzy relation generalizes these degrees to membership grades. So a crisp relation is a restricted case of fuzzy relation. So here in the fuzzy relation, instead of fixed values, here we are assuming that each element has membership value 1, but here there may be degrees of the relation. We say that 2 is less than 3 with a degree 0.2, 2 is less than 4 with a degree 0.4, and 2 is less than 5 with a degree 0.6, etc. So we are assigning graded values. And for example here, x is between 0 and 10. We are considering y values. Beyond this line, the membership has value 0 for the relation. And at this side, as we get closer to the x-axis, membership value is closer to 1, and it gets smaller and smaller, approaches to 0 when we are getting closer to the line y is equal to x. So we have fuzzy graded values. Here, x and y are the sets for which the membership value is 1. However, it may be more complicated if universe of this course is also fuzzy. We have here a fuzzy set for x and also fuzzy set for y. We are trying to define the relation x is less than y on these fuzzy sets. A relation among crisp sets x1 up to xn is a subset of the Cartesian product of x1 up to xn, denoted as the relation on x1 up to xn, or the relation, here we have xi, such that I is between 1 and n. So the relation R on x1 up to xn is a subset of the Cartesian product of the sets. The basic concept of sets can also be applied to relation because they are also sets. For example, containment, subset, union, intersection, complement can be defined also for the relations of fuzzy sets. Each crisp relation can be identified by its characteristic function. So a relation on x1 up to xn has value 1 if the point x1 up to xn is element of the relation, and otherwise, if it is not element of the relation, the value of the relation is 0. The membership of x1 up to xn in R signifies that the element of x1 up to xn are related to each other. A relation can be written as a set of ordered tuples. So the relation on x1 up to xn represents n-dimensional membership array R, which has the indices starting from I1 up to In. Each element of I1 of R corresponds to exactly one member of x1, for the first one, and each element of I2 of R corresponds to exactly one member of x2, and so on. If n tuple from x1 up to xn is element of the Cartesian product of x1, x2, xn, corresponds to a point in the relation, then we are saying that for that point we have value 1 if and only if that tuple is element of the relation and it is 0 otherwise. The characteristic function of a crisp relation can be generalized to allow tuples to have degrees of membership. Recall the generalization of characteristic function of a crisp set. Then a fuzzy relation is a fuzzy set defined on tuples from x1 up to xn that may have varying degrees of membership within the relation. The membership grade indicates the strength of the present relation between elements of the tuple. The fuzzy relation can also be represented by an n-dimensional membership array. Let R be a fuzzy relation between two sets. Set X is containing New York City and Paris, and set Y containing Beijing, New York City, and London. R shall represent relational concept very far. This relation can be written in a list notation as relation xy. We will consider each combination of the elements in set X and the elements in the set Y, and the combination New York City, Beijing has value 1, saying that they are very far, and New York City is not far, has value 0, and New York City, London has value 0.6, Paris, Beijing has value 0.9, they are far, Paris, New York City 0.7, and Paris, London, they are not so far, has value, membership value 0.3 in the relation. It can be also represented as two-dimensional membership array. We have X having elements New York and Paris, and Y having elements Beijing, New York, and London, as given here. And whatever the values, for example, New York, Beijing, this one has value 1, New York has value 0, etc. Let n be greater or equal to 2 fuzzy sets, A1 up to AN, be defined in the universes of this course x1 up to xn, respectively. Let n be greater or equal to 2 fuzzy sets, A1 up to AN, be defined in the universes of this course x1 up to xn, respectively. The Cartesian product of the fuzzy sets A1 up to AN, denoted by the Cartesian product as shown here, is a fuzzy relation in the product space x1 up to xn. It is defined by its membership function. We have a membership function on the Cartesian product for each tuple, and it is defined as a function of the membership values, whereas xi is element of the universe of discourse for xi, I is from 1 to n. Usually, for the Cartesian product, this t is the minimum of the membership functions. Sometimes also the product multiplication. A special case of the Cartesian product is when n is equal to 2. Then the Cartesian product of fuzzy sets, A element of fuzzy set on X and B element of fuzzy set on Y is a fuzzy relation A Cartesian B element of the fuzzy X Cartesian Y, defined by the membership of the Cartesian product of A and B for the point xy has a t operation on the membership value of A x and membership value on B. For each x element of universe of discourse for X and for each Y element of discourse of Y. ST operation, usually minimum is used. Product multiplication also can be used. Let, for example, A be this fuzzy set and B is this fuzzy set. If we take the Cartesian product of A and B, then we obtain such a relation. Notice that for these points, the membership value of A is 0, and then it's increasing, becoming 1, and then decreasing, and after that, it is 0. And similar for the fuzzy set B. And we are trying to find what is the Cartesian product of these two sets. We are taking the minimum of these two sets. For example, consider any point here. Consider the value of the membership in A, it is 0. And for example, here it is 0 for the membership B. We take the minimum of these two, it is 0. So for all these regions, because either this membership or that membership is 0, we have value 0. And for that region, we are considering any point and taking the value on the set A, membership value on the set, fuzzy set A, and also on the set B, and we are taking the minimum of these two values. So we obtain such a shape for the values of the membership in the Cartesian product relation.